So before we start learning about the elements of period 3, we need to recap what we already know about structure and bonding. So I want you to pause the video. I want you to try your best to sketch out the flowchart for different types of structure and bonding and fill it in to the best of your ability. Pause the video now. So if you filled this in, you should have been trying to remember the different types of structure and bonding. So what we're going to start with is we're going to start with if our elements present is a metal, so for example something like sodium or magnesium, perhaps potassium or calcium, then we would say that the bonding is metallic. So we need to be able to define metallic bonding, a strong electrostatic force of attraction between positive metal ions and delocalized electrons. If our exam question asks us for structure and bonding, then our structure is a giant metallic lattice, and you must remember to say giant metallic lattice. That's not the bonding, that's the structure. The bonding is metallic, those electrostatic forces of attraction. So our forces holding our particles together, because this is giant, we're going to say the word strong. So strong, and then electrostatic forces, and they're of attraction, don't just say forces because they're not repulsive, and they're between positive metal ions, and in an exam perhaps you'll say which metal ions, and delocalized electrons. And then if we're looking at the combination of a metal with a non-metal, so maybe sodium chloride, potassium oxide, then we would say our bonding is ionic. That's electrostatic forces between oppositely charged ions. We'd say our structure is a giant ionic lattice. And so we'd say our forces are strong electrostatic forces, and again we must say of attraction between oppositely charged ions, and always remember to, in an exam question, say what those are. So sodium ions and chloride ions. Do be careful though, make sure you call the ions by their appropriate names. And then our last one, if our element is non-metal only, so we're talking sulfur, phosphorus, carbon, then our bonding is covalent, but our structure could be two types. We could have giant covalent, or you might want to call that macromolecular. Or we could have simple covalent, or simple molecular. Now if we're giant, then the forces holding it together, because it's giant, can you see that commonality? Giant, strong, giant metallic, strong electrostatic, giant ionic, strong electrostatic, giant covalent, strong covalent bonds. And actually it's good to say many because it's happening over and over and over again. Whereas if we're simple, we've got weak intermolecular forces. And those weak intermolecular forces could be van der Waals, they could be permanent dipole, or they could be hydrogen bonds. And depending on the situation will be what we have to discuss. So we've had a review of that, we can leap into our elements of period 3. So if we have a look, pause the video again and see if you can fill in the types of structure for the different elements in period 3. Now bearing in mind we've just filled in this flowchart, it should be fairly easy. Now one of these is not going to be used with the elements of period 3. And given that the definition of an element is made of one type of atom only, what of these colours of this flowchart could not be used in the elements? So we can't be using ionic because we can't have two different elements if we're just talking about the straight elements of period 3. So let's have a look. We've got the first three, sodium, magnesium and aluminium. We would be looking down our red of our flowchart. They are all metals, so their structure is giant metallic lattice, which means that the type of bonding is metallic, and you could put that definition in, and the type of forces here, strong forces of attraction between positive metal ions and delocalized electrons. And then if we're looking at silicon, silicon is a macromolecular, because remember silicon and diamond in group 4, macromolecular with covalent bonding between the atoms, and we would have strong covalent bonds between, so what are they between? In this case, they're between the Si atoms. Okay, and then we've got P4, S8 and Cl2, and do remember that we do need to know these formulas. These are not monoatomic, these have got different formulas. These are all simple molecular or simple covalent with covalent bonding, but it's not the covalent bonding that you break when you boil them or melt them, it's the weak intermolecular forces, and then because these are all elements, these would all be van der Waals forces. And these are all molecular, P4, S8, Cl2, so van der Waals forces between molecules. Now Ar's out on its own because it's not a molecule, because it doesn't have a covalent bond in it, so it's simple atomic, it doesn't have any bonding, but it would have van der Waals between the atoms. Those electrons will move to one side of the atom and create a weak force of attraction to the next atom. As a result of that, what we can see is that we've got 4 things to the left that have got strong forces, and so they would have high melting and boiling points, and we've got 4 things to the right that have weak forces, so they would have low melting and boiling points. I want you to pause the video now again, and I want you to see if you can remember the trend in atomic radius, so the size of the atom as you go across a period. So what you should have remembered is as you go across a period, there are more protons in the nucleus. But the electrons are being added to the same shell, so the shielding is very similar. And so therefore, although you might think it's got the same shells and it's the same size, because there's more protons attracting that shell, then the attraction is increasing, and because the attraction is increasing, the size decreases. They're being held in tighter. So again, have a little pause of the video and see if you can remember the trend in first ionization energy. So what we should have remembered is, again, as you go across the period, there are more protons in the nucleus. They're adding to the same shell, those electrons, so we've got similar shielding, but the attraction increases. Now, if the attraction increases, the amount of energy we need increases. There are some exceptions to this. What you need to remember is that pattern of that graph, it goes, for any period, it goes 2, like up for 2, little dip, up for 3, little dip, up for 3. So our pattern goes group 1, group 2, dip. So why are there some exceptions? So there's an exception. The first exception would be here at the first dip, and then the second exception would be here at this second dip. That first exception in period 3 would be aluminium, and our second exception in period 3 would be for sulfur. So why have we got these exceptions? So our first one, it's a new subshell, higher in energy. So we're going, if you think about the electron configuration, we're going 3p1 for aluminium, whereas magnesium before it was 3s2. And the aluminium's outer electron is in a new subshell, it's higher in energy. And then for sulfur, we've got a pair in a 3p orbital, and that causes a repulsion. So they repel, and then that makes that a little bit easier to remove as well. And what's our trend in electronegativity? More protons, similar shielding, stronger attraction. So it's attracting the shared pair more strongly, and so our electronegativity increases as we go across, remembering that the last element, a noble gas, doesn't have an electronegativity value because it doesn't form bonds. So that's our first little video revising what we knew from before. It might be worth going to your recall pack now and practicing some questions.